And I'm Tom.
I'm Thomas, and we're Team 13. This is our project for embedded systems. Our project is based on the Greek myth of Theseus and the Minotaur. The Minotaur is a half-man, half-bull monster that devours any creature who wanders into its labyrinth. And Theseus is a Greek hero who is sent to the labyrinth to find and kill the Minotaur. Once he's done this, he uses a ball of yarn that he's laid as he is searching for the Minotaur to safely get back out of the maze.
So to sort of recreate this for our project, we made this board here that sort of represents the maze. And in the board are two automated rovers, one of which is the Theseus rover, which basically goes through the maze and builds a map of the maze and to know where he's been and to search through it. And instead of finding the Minotaur and killing him, we actually made it so that he's going into the maze and leaves that trail behind him and then finds a treasure. And when he finds the treasure, he has a path back out, and that's how he wins the game.
And the other rover will be the Minotaur. His mission hasn't changed. If he sees anything, Theseus in this case, he'll kill it.
So we used a line follower sensor, which was just 8 IR LEDs that were built into an array and communicated with the PIC via I2C. The data that this read was an 8-bit number, and the 8-bit number is just basically which of the LEDs are currently being lit. And when LED is lit when a black line is under it and it's lit.
So I'll give you a quick run through. Right here, the middle two LEDs will be lit, so that'll say you can go straight. It's going straight, and then once it starts moving to the right or left, either of these would be set off, saying that you would need to now veer to get back, to readjust back onto the line. Now it sees that you can go left by seeing that these 4 LEDs are lit. Now once it sees that, it goes into a slightly forward state, which will just go slightly past the line so it can make an even turn in this situation. So once you keep driving, you see that it can go into a tick. It sees a tick. A tick just is a way that we update the UI. You keep going straight, and once it sees that you can make a turn here, then it goes into the same slightly forward state. Now in this situation, the slightly forward state will collect data for 200 milliseconds. Now over the 200 milliseconds, it will collect the data and update the options every single time, or it'll keep every option. So here, after the 200 milliseconds, it'll see that straight's an option here. And then there we know that you can go right, left, or straight.
So I'm going to be talking about the motor thread. The motor thread only responds to messages that are relayed through the line follow thread. Some of these messages do originate from the controller PIC, but they are routed through the line follower to the motor thread. So the motor thread has 8 states. The main ones are the stop and the forward state. When it's stopped, the motors are off and the direction is forward. And then for the forward state, the motors are 100% forward and the direction is forward as well. From the stop state, depending on the message received, it can go to the slight forward, turn left, turn right, turn around, or forward state. If we're getting a turn left message, then I stop looking for messages from the line follower until I'm done with the turning left. And turning left just sets both of the motors to 100%, and then the right motor to forward and the left motor to back. This is reverse for turn right, and then the turnaround is simply 2 left turns in a row. We only ever turn in 90 degree or 100 degrees. And so the turn left, turn right, and turn around would happen at intersections for the turn left and turn right, and then a dead end for the turnaround. This slight forward state is entered into as the line follower senses that we come up to an intersection, and then we go into the slight forward state to determine if all the options at that intersection, and then we return to the stop state to wait for a message from the control queue on which way to go. When we're in the forward state, internally I'm using encoders to try and make sure that we're going straight. So if one encoder, we have a count for the left encoder and the right encoder, and if one is less than the other, it will speed up or slow down the one with the greater count to 80% speed until the encoder counts are equal, and then it will speed them both back up to 100%. But in addition, the line follower will be sending me messages if I'm too far left of the line or too far right of the line. And so then, once we're in the adjust left state, we set the left motor to about 30% power and the right to 100% until we receive this forward command again, and then we go to the forward state. Similarly, for the adjust right, we set the right motor to 30% power and the left to 100% until we receive another message that says, okay, now we're on the line at square with it, and we go back into the forward state.
To control and sort of decide where the two rovers go throughout the maze, drawn up this sample maze, and basically what happens is we have the Theseus starting point and the Minotaur starting point, which are sort of independent of each other. And so each rover will have its own internal map of what's going on in the maze and where it's been. So basically the search algorithm. And so when the game starts up, Theseus will be in a start location. He'll be told, okay, all I can do is go forward. So he's going to move forward into this first location. And then we're going to mark that with 1, meaning he's visited that location once. So once he's here, so he has two options now. He can go right or he can go forward. Neither place has been visited before. So these empty locations are going to be denoted by 0, or 0 visits. And so basically he's going to choose one at random because it doesn't really matter where he goes. He's just searching and like trying to find things at this point. So he comes down here, draw another 1. And so he keeps doing this and he keeps going. He says, all right, I have these options. So he comes down, keeps drawing 1s, chooses random in each location, and then he gets to a dead end. So when he gets to a dead end, normally he would just turn around. But at this point, he's going to mark that with another 1, so he's going to increment the visits just to keep him from going back there. And then he's going to come down. He's going to go to 2, and he's going to get back to this 1. But when he gets back to that 1, he still has locations that he hasn't visited before, so he's not going to increment there. He's going to go to those, and he gets to another dead end. So now he's backtracking, and he gets here, and now there's no unvisited locations that he can go to, so he marks that with another 1. So say right here we have the treasure that he's looking for. So he's going to keep searching, just 1. And so he gets this treasure, he marks the 1, and then, so the Pi control system at this point is going to say, hey, you found the treasure. He's no longer looking for the minimum. To get out of the maze, he has this nice trail of 1s, so he's just going to go and he's going to say, all right, right here, I've visited that 1 time. He'll come out, he'll write a 2 there, write a 2 here, write a 2 here. And so he's just choosing this trail of 1s, comes back out, follows it, and now he's back at the start, and he's won the game. So the Minotaur does pretty much the same thing as Theseus did when he first entered, but he's got a little bit more knowledge, and basically he's just going to keep going, and he's just searching. To carry out the actual movement of the rovers throughout the maze, we had 2 PIC32 microcontrollers, one of which was our motor control, and that basically just took your line follower data and used it to drive the physical motors, as well as receive messages from the control PIC32, which would take these options messages, which is basically a request for a decision, and use Tremo's algorithm in its current board status to say, hey, take a right here, you haven't searched here, or hey, turn around, we're trying to exit. So there's a main control system that we would run to do all this, which is our PI control. And basically it had two main components, which were our game control, which carried out the actual gameplay, and our comm control. So our comm control could also be run sort of headlessly. It would basically create a thread, or a system of threads for each of the four PIC-32s and their Y-flies. And start a receive thread, a transmit thread, and a ping thread. So the receive would take in messages, do some error handling, then route them to the desired destination, whether that was actually the Raspberry Pi or another PIC. And then the transmit would just take this queue of all the messages people were trying to send it and send it to that PIC-32 or that Y-fly. And then so the other component was the game control. And that was where a lot of the intelligence on the Pi side came from and the game over conditions. Basically, it would sit there, and anytime the communication controller received a message that was going from one of the, so Theseus controlled a Theseus motor, or Minotaur controlled a Minotaur motor, it would take that, send it to the PI control, or this game control system, which would say, okay, it said it's going to the right, and so it would move either the Theseus or the Minotaur location, and then it would perform a couple checks. One, say, did you get the treasure? If it did get the treasure, it would signal to Theseus, say, hey, start exiting. Or it would check to see if the game was over. So if the Minotaur had killed Theseus, or if Theseus had exited the maze, in which case it would send a kill signal to all the boards, and that would be your game over.
This is the standard message that's being sent. It's a 4-byte message. 1 byte being made up of the source and destination. The next byte, sequence number. The next byte is the data we're using. And the last byte is the checksum. The checksum is used to check the validity of the message. They just checked at the Pi side and the PIC side. Next is the data that we were sending, just to that's being used. Sequence number is to make sure that we're never using a duplicate message, because we send a message multiple times, just to make sure that it gets through.
These are some of the problems we had, or that we encountered as we were doing the project. One of the big ones was the ticks versus turns, and determining when we're coming up to a tick that it's not in fact a turn or an intersection, because the line follower looks sort of like an intersection. So one of the ways we combated that was that we made the tick shorter, and we think in addition that we could have done a tick on only one side of the line. Also, with the ticks, there was an issue that if we were not perfectly perpendicular as we came across the tick, one tick would be read first, and then the other tick would be read, so that the controller would think that we were 2 squares ahead instead of just 1.
So really the biggest problem that we had, which is kind of most apparent in our final demo, was communication. I think the big issue here was mostly just that the Pi had so much going on it, especially after we moved a lot of the functionality up to the Pi. And then on top of that, we had tried to write our own TCP server, and I think what helped us was using a pre-made TCP server, such as the Qt version, and that would kind of just give us a more reliable system that we could depend on without having to debug our own. Then the line follower was a big point of issue, which it was great because it did all of the ADC and stuff for us, and it did debouncing, so we could just trust on this value every millisecond. But one of the big issues that we had was you'd be following a line, and saying like, all right, if I get something that's different than my current reading, then go to some other state. But every now and then we'd get this strange 0, 0 reading from the line follower, so we kind of had to account for that and just ignore it in situations where it wouldn't make sense to get it. Overall, I think we were able to overcome most of this, and I think given an extra person or a couple days more time, we would have